molecular geometry, and VSEPR. In this section, we are going to explore some fundamental concepts that are crucial for understanding molecular structure and reactivity in organic chemistry. Let's begin by discussing how organic chemists analyze the bonds in molecules using the valence shell electron pair repulsion theory, or VSEPR. This model is going to help us predict molecular geometry based on a simple but powerful principle where electron pairs repel each other, causing them to position themselves as far apart as possible. The VSEPR model is particularly valuable because it's going to give us a first approximation of molecular structure. But it's also important to note down that VSEPR has got limitations, particularly when dealing with antibonding molecular orbitals. Let's start with methane, which is our very first example here. Now, in methane, we have got like 4 carbon-hydrogen bonds, and the most important thing with these carbon-hydrogen bonds is all of these bonds are going to be equal in length, which is going to be about 1.10 angstrom. And also the bond angle here is going to be 109.5, which is definitely going to make it or give it a tetrahedral arrangement. Now, this perfect tetrahedral arrangement is going to raise an interesting question. How does carbon form 4 bonds when it has got only 2 unpaired electrons in its valence shell? Now, when we look into the valence shell, this is how it's going to be. So let's draw the electronic configuration of carbon. So it's going to be 1s2, 2s2, 2p2, because carbon has got like 6 valence electrons. And this is going to be our 2s orbital, and this is going to be the 2p orbital. Now, the 2s orbital is completely filled, whereas the 2p orbital, we need to make sure that we fill it with at least 1 electron before we pair it up, according to Hund's rule. Now, what is the reason? How can carbon form 4 bonds when it has got only 2 unpaired electrons here? Now, the answer is going to lie in the concept called as orbital hybridization, which was first proposed by Linus Pauling in 1931. Now, what actually happens here is one of the s electrons is going to go get shifted onto the p orbital. So it's going to get promoted onto the p orbital. But that alone is not going to explain why all the bonds are identical. The key thing here is carbon is going to use hybridized atomic orbitals. They're going to use sp3 hybridized orbital. They're not going to simply use the s orbital. They're not going to simply use the p orbitals, but they're going to get all these s and p orbitals are going to hybridize together, which means they are going to mix together and they're going to form new hybridized orbitals, which we are going to call as the sp3 hybridized orbital. Why? Because there is one s orbital and there are 3 p orbitals, which when they are going to be combined, they're going to give us the sp3 hybridized orbitals. And this is how it's going to happen. This one s orbital and then these 3 p orbitals are going to hybridize together to give 4 new sp3 hybridized orbitals, and each of these 4 sp3 hybridized orbitals is going to have 25% s character and 75% p character. Here we can take a look into the picture to see like how the sp3 hybridized orbitals is going to look like. So this is our s orbital, which is spherical in shape. And then here is our p orbital, which is dumbbell shape. When they mix together, it's going to form the sp3 hybridized orbital, which is going to have 2 lobes created when the s orbital is going to add to 1 lobe of the p orbital. And this lobe is created when the s orbital is going to subtract from the lobe of the p orbital. And this larger lobe is used for forming covalent bonds. These sp3 hybridized orbitals are going to arrange themselves in a tetrahedral pattern, as what we see here, in order to maximize their distance from each other, so as to create the characteristic 109.5 degree bond angles, is what we see in the case of methane. Let's go on to a slightly more complex molecule, ethane. Let's examine the structure of ethane here. In ethane, there are 2 carbons, and each of these 2 carbons has got 4 sigma bonds, right? So this has got 4 sigma bonds as well. And because of this, each of these carbons is going to have the tetrahedral arrangement. And each carbon is going to use its sp3 hybridized orbitals to form bonds. So let's take a look into this carbon right here, the first carbon. It has got like what we have seen in the case of methane. This also is going to have 4 sp3 hybridized orbital. But out of the 4 sp3 hybridized orbital, 3 will be used to form a bond with 3 hydrogens, right? And the remaining 4th sp3 hybridized orbital will be used to form a bond with the other carbon, right? And the same thing is going to happen with this carbon. So this carbon again has got 4 sp3 hybridized orbitals, and 3 of them will be used to form the bond with 3 hydrogens. Now, all of these bonds that you see here in ethane are sigma bonds, which are cylindrically symmetrical and also formed by end-on orbital overlap. Let's explore the formation of double bonds using ethylene as our example. Here, the carbons in ethylene is going to require a different kind of hybridization pattern, which we call as the sp2 hybridization. Here, each of these carbons is going to hybridize only 2 of its p orbitals with its s orbital to create 3 sp2 hybridized orbitals. The remaining p orbital is going to be left unhybridized. Here is the top view and side view of these orbitals, where we could see that the 3 sp2 hybridized orbitals are going to be lying in the same plane, whereas the unhybridized p orbital is going to be lying perpendicular to this plane. In the structure of an alkene, we can clearly see that there is a double bond. Out of these 2 bonds, one bond should be a sigma bond and the other bond should be a pi bond. The sigma bond is formed by the overlap of the sp2 hybridized orbitals, which is present in these 2 carbons, whereas the pi bond is formed by the overlap of the unhybridized p orbitals. This is basically going to be side-to-side overlap of the 2 unhybridized p orbitals, and it's going to exist as one lobe above the plane and the other lobe below the plane. And this is going to push all of these 6 atoms to be in the same plane. Finally, let's examine triple bonds using acetylene molecule as our example. Here, each of these carbons is going to use sp hybridization, which means only one p orbital is going to hybridize with the s orbital to create 2 sp hybridized orbitals. The remaining 2 p orbitals are going to be left unhybridized. Here is a pictorial representation of these orbitals, where we can see that the hybridized sp orbitals are going to be lying in the same planes, whereas the unhybridized p orbitals are going to be lying perpendicular to each other. So this is an unhybridized p orbital, and there is one more unhybridized p orbital, which is going to be in perpendicular direction with respect to each other. And when we look into the structure of acetylene molecule, we can clearly see that there is a triple bond, and the bond angle here is going to be 180 degree, which means the structure here is going to be linear. The molecular geometry here is going to be linear. And out of these 3 bonds, one is going to be a sigma bond, which is going to be formed by the sp-sp overlap of the orbitals that's present in these 2 carbons. And the other 2 is going to be pi bonds. So there are going to be 2 pi bonds, which are going to lie perpendicular to each other. So that's one pi bond, and this is going to be another pi bond, and they are going to be formed by the overlap of the unhybridized p orbitals present in the 2 carbons. Relationship between hybridization, bond angle, bond length, and bond strength. The progression from single to double to triple bonds is going to show an interesting trend here. As the number of bonds increases, the bond becomes stronger and as well as shorter. Now, this can be seen from this chart here. Our focus is going to be on these 2 columns right here, which is the length of the carbon-carbon bond and the strength of the carbon-carbon bond. So as we go from ethane to ethylene to acetylene molecule, we can clearly see that the bond length is actually decreasing. So the bond length is decreasing, whereas the bond strength is getting increased. So which means as the length of the bond is going to increase, the strength of the bond is going to decrease. And this relationship between bond multiplicity, strength, and length is crucial for understanding molecular stability and reactivity of the compound. One more thing that we can derive from this chart is with the increase in the s character of the orbital, there is going to be an increase in the bond angle. Let's take the first case. We have an sp3 hybridization here for the ethane molecule, where we could see that there is 25% S and 75% P. So with that, our bond angle is 109.5 degrees. But in the case of sp2, it's going to be 33% of S and 66% of P, which is going to increase the bond angle to 120 degrees. But with sp hybridization, where we have 50% s and 50% p, the bond angle is drastically increased to 180 degree. So with increase in the s character of the orbital, we can easily tell that there is an increase in the bond angle and increase in the strength of the bond, but decrease in the length of the bond.